So we now have an algorithm, a very elegant one, that solves the weighted independent set problem in path graphs. Moreover, the algorithm runs in linear O of n time, clearly the best possible. But before we do a victory lap, I want to point out that there's something this algorithm doesn't do that you might want it to do, namely hand you the actual optimal solution, not merely the value of that optimal solution. So the point of this video is to show you how we can reconstruct an optimal solution given the table filling algorithm from the previous video. So let me just write that algorithm back down. It's so short it won't take me too long. Now when this algorithm completes, what do we have in our hands? We have an array, and this array is filled with numbers. So in particular, in the last entry of the array is a number like 184. So that's great. That tells us that the maximum weight that any independent set possesses is 184. But in many applications, we're going to want to know not just that information, but actually which vertices constitute that independent set with total weight 184. So perhaps the first hack that comes to mind to address this issue is to augment the array so that each entry stores not just the value of an optimal solution to the subproblem induced by the graph G sub I, but also an actual set of vertices achieving that value. And I'll leave it for you to, if you want, rework the previous pseudocode so that when you fill in a new entry, you fill in not just the value of an optimal solution given solutions to the previous subproblems, but in fact also the solution itself. This hack, however, is not generally how things are done in dynamic programming. It unnecessarily wastes both time and space, and a much smarter approach is to reconstruct from the filled-in table an optimal solution as needed. So if you think about it, it's kind of cool that this is even possible, that our one-line algorithm doesn't cover its tracks, that it leaves us clues for us as detectives to go back and examine and reconstruct what the optimal solution is. The following key point articulates exactly why this is indeed possible. So the starting point of this observation is the correctness of our algorithm, our one-line algorithm, which, of course, we established in the previous video. And by correctness, I mean it's guaranteed that this algorithm will populate each entry of the array correctly. The number in the ith entry is indeed the maximum weight of an independent set in the graph GI. So remember our thought experiment about what the optimal solution could possibly look like. We concluded it could only be one of two things, and we really wound up wishing we had a little birdie that could tell us whether or not the rightmost vertex v sub n was in the optimal solution or not. If we knew which case we were in, we could just recursively compute the remainder of the solution from a graph that has either one or two fewer vertices. So here's the point. This filled-in table, that's our little birdie. Here's what I mean. Well, what's the reasoning that our algorithm goes through to fill in this last entry of this array? And don't forget, we've already proven that our algorithm's correct. We did that in our last video. Well, it does a comparison between the two possible candidates vying for the optimal one. On the one hand, it computes the case 1 solution. It looks up the optimal value of a solution from the graph with one fewer vertex, and it compares that to the case 2 solution, including Vn, the last vertex, and adding that to an optimal solution with two fewer vertices. And in this max operator in the line of code, it's explicitly comparing which is better. Case 1, the solution which excludes v sub n, or case 2, the solution which includes v sub n. So whichever one of those was the winner, whichever one of those cases was used to fill in that last entry, that exactly tells us whether or not v sub n is in the optimal solution. If we use the first case, that means v sub n is not in the optimal solution. It gets excluded. If the second case was the winner, then we know v sub n is in the optimal solution because that was the winner. If we have a tie, then there's an optimal solution either way. There's one that includes vn and there's one that excludes vn. So those are the tracks in the mud left for us by the forward direction of the for loop. We can just go back and look which case was used to fill in each entry of the array. Again, for the ones that used case 1, that corresponds to excluding the current vertex. For those that used case 2 to fill in the entry, that corresponds to including that vertex in the solution. So the Reconstruction algorithm will take as input the filled-in array that was generated by our one-line algorithm on the previous slide. And what it's going to do is it's going to trace through this array from right to left. And at each step of the main loop, it's going to look at the current entry, and it's just going to compute explicitly which of the two candidates were used to fill in this array entry. If you want, you could also cache the results of these comparisons on the forward pass That's an optimization that will be useful later for harder problems. But for now, if you want, you can just think about redoing the comparison, saying, hey, there were two possible ways that we could have filled in this entry. Let's just check which of the two were used. So if, in fact, the preceding array entry is at least as large as the one from 2 back plus the weight of the current vertex, that corresponds to case 1 winning, to the subsolution that excludes the current vertex being better than the one that includes it. So in that case, we just skip the current vertex v sub I, and we decrease the array index by 1 in our scan. If the other case wins, that is, if we fill in the current entry, if an optimal solution to the current graph G sub I comprises the current vertex V sub I plus the optimal solution to the graph with 2 fewer vertices, in this case, we know we better include V sub I. That's part of an optimal solution to the current subproblem. Moreover, that's the case where we need to look up the optimal solution with 2 fewer vertices. So we include the current vertex and we decrease the array index by 2. So formally, we have a correctness claim, which is that the final output capital S returned by the reconstruction algorithm is as desired a maximum weight independent set of the original graph G. We've already talked about all the ingredients necessary for a formal proof for those of you who are interested. Of course, it proceeds by induction, and in the inductive step, you use the same case analysis we've been using over and over again. The optimal solution at any given point, it has only 2 possible candidates. The algorithm explicitly figures out which of the 2 that it is, and that is what triggers whether or not to include or exclude the current vertex. The running time, it's even easier. We have a while loop. It runs at most n iterations. We do constant work in each of the iterations. So just like the forward pass, this backwards pass is really just a single scan through the array. It's going to be lightning fast linear time.